In the last part of this chapter, I'm going to discuss RC circuits, namely charging and discharging a capacitor. Let's start with charging process. So for that, I'm going to have a very simple circuit. Here we have a battery, a resistor, a capacitor, and switch, which is open initially. Let's first close that switch. When we do that, the current generated by the battery will start to flow around throughout the circuit. As current flows, charge will begin to build up on this capacitor, and eventually voltage drop on the capacitor will be equal to the EMF. At this point, the current will stop flowing. This is the big picture actually. But we can also write a detailed formulas for what happens moment by moment. The potential, the charge, and the current as a function of time. You need to remember a few key formulas that are very important for this part. So when they are in series, then we can express epsilon as sum of these two potentials, VR plus VC, and VR is I times R, and VC is Q over C, and we know that the current is rate of change of charge, that's dQ over dt. It's positive because the amount of charge on the place of the capacitor is increasing. Then epsilon can be expressed as I times R, which is dQ over dt times R plus Q over C. And we need to solve this equation, but in order to solve this equation, we have to reorganize it. I can re-express this equation as epsilon times C times dt. So it's very easy to obtain that, which equals RC dQ plus Q dt. So you can get this equation from here. So it's not a big deal. I'm going to move this dQ dt to the left. So I have EC minus Q times dt on the left, and I have RC times dQ on the right. Then I'm going to reorganize this equation as dQ over epsilon C minus Q, and on the right side I have dt over RC. Okay, so then to solve this equation, I'm just going to take the integral of both sides from 0 to Q and from 0 to T, because initially at time t equal to 0 there is no charge. So the integral of this part is minus ln epsilon C minus Q from 0 to Q, and the right side is just T over RC from 0 to T. So when you put these limits, then you get minus ln epsilon C minus Q minus ln epsilon C, and on the right side we have just T over RC. I'm just going to multiply both sides with minus. Then I get ln epsilon C minus Q minus ln epsilon C, and I have minus T over RC. So this is ln A minus ln B, which is ln A over B. Therefore, let's rewrite this equation as ln A over B, which is epsilon C minus Q over epsilon C, and I have minus T over RC. Let's simplify this equation. So epsilon C cancel out. Then we have ln 1 minus Q over epsilon C. Then we have minus T over RC on the right side. So if you take the exponential of both sides, then you get rid of this ln form. Then we have minus Q over epsilon C. And on the right side, we have E2 minus T over RC. From here, we can get Q as a function of time, which reads as epsilon C times 1 minus E2 minus T over RC. So this is one of the most important equations in the charging process. Actually, we have two important equations in this part. The first one is this one, IR plus Q over C is epsilon, and this is the second one, Q as a function of time. Let's have some discussion on Q. Now let me rewrite this equation again. So this will be our starting point. Then let's define a tau, which stands for time constant, and which is R times C. The unit is just time, second. Now sometimes this equation is expressed as a function of tau, which is epsilon C1 minus E2 minus T over tau. Now we want to see what happens to Q as a function of time. So let's start from the beginning. At time t equal to 0, let's start with our main equation or the master equation. So when you put t equal to 0 here, this part becomes 1. So 1 minus 1 is 0, so Q is 0. So there's no charge initially. This is what we expect, right? So when time goes to infinity, so this is not a real infinity. It's just a long enough time for this capacitor to get fully charged. In some situations, just 10 seconds. In some cases, it's 20 seconds, 100 seconds, 500 seconds, and so on. Now, this is our main equation. So when you put t infinity here, that part will be e to minus infinity, which is 1 over infinity, and the result is 0. So that part will disappear. So the charge is just epsilon times c. So this is the maximum value you can get, actually. Now, when you plot charge as a function of time, you see there is an increase. So we start at 0 and we end up at maximum value. But this increase is exponential. It's not linear. So we start from 0, time t equal to 0, there is no charge. Then it increases exponentially and saturated at some time later. So this charge here, the maximum charge, or epsilon times c. Well, then we can re-express this main equation in terms of Q max. So that's Q is Q max 1 e to minus t over RC. Sometimes it's very useful to use this equation. We'll see that when we discuss some example. Now let's see what happens at time constant. So when t goes to RC, or when t is RC, then Q is, so this part e to minus 1. So you get 1 minus 1 over epsilon. So this part becomes 0.63. The charge for this specific time is 0.63 epsilon c. So that means this is the 63% of the maximum charge. So what I mean, at time t equal to RC, you get 63% of the maximum charge. Well, by the way, you don't have to memorize all these derivations. That's not necessary. It's better to know these two forms. This is the first one. Epsilon is IR over QC. And this is the charge as a function of time. Now, in the second part, I'm going to analyze VC, voltage across the capacitor. So again, let's write down our main equation or the master equation. And we want to see what happens to VC as a function of time. So VC is Q over C. So we already know Q is right here. So C is cancelled out. Then we get VC as epsilon times 1 e to minus t over RC. So it's very simple. So you don't have to memorize this equation. Once you know charge, then you can get VC. We can see what happens at time t equal to 0. So again, at time t equal to 0, that part will disappear. So there is no potential across the resistor. Initially, there is no charge on the capacitor. And then time goes to infinity, again, this part will disappear and you get VC to be epsilon. Again, there's increase, and this increase is exponential here. So we have the same kind of exponential function here. So this is the maximum voltage you can get for the capacitor. Now for the current part, again, let's start with the main equation. So we already know that current is dq over dt. And we just want to know what's going to happen to current as a function of time. So when you take the derivative of this charge with respect to time, you get the current as epsilon over r e to minus t over rc. Let's see what happens at the limiting values. So at time t equal to 0, that part becomes 1. So then we have epsilon over r, which is the maximum value we can get. So at time t equal to infinity, that part becomes e to minus infinity, which is 1 over infinity, and the whole thing will disappear. That means at time t equal to infinity, there will be no current. This is what we expect, actually. So we start with maximum current at time t equal to 0, and then as time goes on, the current decreases. So the current is decreasing as a function of time, but this decrease is exponential. So we have this exponential decrease. So initially we have a maximum current, which is epsilon over r. At time t equal to infinity, or at very long time, then current will disappear. So then we can re-express this equation in terms of the maximum current. Then we can have I max e to minus t over RC. sometimes it's very helpful to use this equation. Now let's see what happens at time t equal to RC. Let's have our current equation. So when you put RC here, then you get, so this part will become E2 minus 1, so which is 1 over E. 1 over E is 0.37. So you get 37% of the maximum current. So at time t equal to RC, you will get only 37% of the maximum current. Now let's see what happens in the discharging process. For the discharging process, I'm going to consider the previous part. Let's imagine we have a fully charged capacitor. That means wait long enough to get a fully charged capacitor. And then we open the switch and remove the battery, then reconnect everything. If you do that, then we get this circuit. Now you see we don't have any battery here, but we have a fully charged capacitor. Let's close the switch. So when we do that, the capacitor here is going to behave sort of like a battery. It's going to provide the energy which allows the current flow through the circuit. So this is the direction of discharging current. Now you see R and C are in series, so VR must be equal to VC, and VR is I times R. So this is Q over C, but here charge is decreasing, so I is minus dQ over dt. Now let's re-express this equation. Minus dQ over dt times R is Q over C. So it's very easy to get the solution of this equation. Now I'm going to have RC times dQ on one side and minus Q dt on the other side. Then I'm going to reorganize this equation as dQ over Q on the left and minus dt over RC on the right. Then I'm going to take the integral of both sides. From Q0 to Q, we start from Q0 because now we have a fully charged capacitor. So this is our maximum charge. Then on the right side we have integral from 0 to t. Because at time t equal to 0, the charge on the capacitor is Q0, the maximum charge actually. So the integral of this equation is ln Q from Q0 to Q, and I have minus T over RC again from 0 to t. Then we get ln Q minus ln Q0 and minus T over RC on the other side. So again, this is ln A minus ln B. We can express these as ln Q over Q0 and minus T over RC. I'm gonna take the exponential of both sides. Then we're left with Q over Q0 on the left side and E2 minus T over RC on the right side. So from here, Q is Q0 times E2 minus epsilon RC. So this is the charge as a function of time for a discharging process. Let's analyze Q. So this time our main equation is Q0 E2 minus T over RC. We're going to see what's going to happen to Q as a function of time. Okay, at time t equal to 0, that part becomes e to 0, which is 1. So Q is just Q0 at time t infinity. And this part becomes e2 minus infinity, which is 1 over infinity. Then Q becomes 0. So you see, we start with the maximum charge, then we end up with 0 charge. So there's a decrease, and this decrease is exponential. When we plot charge as a function of time for discharging process, then we have this picture. Or I can re-express this as Q max E2 minus RC. So for t at time constant, again this part becomes E2 minus 1. So this is 0.37 of Q0. When you put this here, we get this. So you see, at time t equal to RC, we are left with only 37% of the maximum charge or the initial charge. Now let's analyze VC. Start with the main equation. We want to see VC as a function of time, so VC is Q over C. Well, we already know our Q. Then VC is Q0 over C times e to minus t over rc. Well, at time t equal to 0, again, you have the maximum voltage across the capacitor, and then at time t equal to infinity, that part will disappear, so Vc will become 0. Then again, we're going to have exponential decrease. So this can be also written as V0 e to minus t over rc. So this Q0 over c will be our initial potential for the capacitor. So when we plot Vc as a function of time, so at time t equal to 0, that part becomes 1. This will be our maximum voltage for the capacitor. At time t equal to infinity, again, this part will disappear. So there will be no potential across the capacitor. So again, there's this exponential decrease. So when we plot Vc as a function of time, we have a very similar picture. So at time t equal to rc, we get 37% of V0. For current, start with the main equation. Again, I as a function of time. So now I is minus dq over dt. When you take derivative of charge with respect to time here, you get I as a function of time. That's q0 over rc e to minus t over rc. This can be re-expressed as v0 over r, because q0 over c is v0, times e to minus t over rc. Well, so again, there will be an exponential decrease here. So when we plot I as a function of time, we get very similar picture. So let's also see what happens at time equal to rc. And we have the same value, 37% of the current becomes available at time t equal to rc. If you like, you can re-express this equation as I0 e to minus t over rc. And they're all the same. Now we are done with discharging process. Let's have a summary. In the circuit, I have charging and the discharging process. So for the charging process and for discharging process, I'm going to use the same picture. But now, if you have the switch in this position, then the process is called the charging process. Now we have a battery, we have R, and we have C. And the current produced by the battery is called charging current. It's moving around clockwise. So here I is dq over dt is plus, because the charge on the capacitor is increasing. Now when we discuss this charging process, then we have switch in this position. We are sorting out the battery, but we have a fully charged capacitor. But the direction of current actually is opposite. This is the discharging current. And here I is minus dq over dt, because the charge on the plates of the capacitor is decreasing. So let's remember Q as a function of time and current as a function of time for charging process. But you see, at time t goes to infinity, or at a long enough time, current becomes 0. So there will be no current passing through R. Now for discharging process, we have charge as a function of time. We have current as a function of time. They are very similar, but there's this minus sign. So for that, I just put my current here, because I is minus dq over dt. So they are reversed actually. They are not on the same side. Now let's combine these two information. Q is a function of time for charging process. The equation for the charging process, epsilon c1 e to minus t over rc. So when we plot these, we get this picture. Now for the discharging process, again, Q is a function of time. Q is q0 e to minus t over rc. And there's an exponential decrease. So at time t equal to 0, we have a maximum value, and then it becomes 0. So right here, t infinity of the charging process, actually t0 of the discharging process. When you put switch from this position to that position, then discharging process will start, but will start at the maximum charge. So these 2 points actually are merging. These 2 points here have the same value. You see right here, time t equal to infinity of the charging process and time t equal to 0 of the discharging process are the same. So Qmax of charging process at infinity actually is the same as Q0 of discharging process at time t equal to 0.